Alright, so this is MathStat341 lecture 13. So what we're going to be doing today is we're going to be doing some consequences of joint minimum variables. And so I'm not going to go through some of the standard examples of joint probability distribution functions because you can go look at them in the book. If you have questions, let the TA know, let me know. I want to try to use class time effectively. So I'm not going to be writing down all the different cases and whatnot. I want to focus on some of the great results. One of the things you need to learn when you're taking a class is if your professor likes something a lot, you should probably like it at least for that semester. Okay, so if I had to rank my favorite concepts in this class, I love generating functions. We're going to see later just how powerful they are. But the method of linearity of expectation is truly phenomenal for how many things it allows us to solve in a good way. So this is one of the big points of the class, is that if you have a complicated problem, you can often figure out the expected value without too much trouble. What else would you like to know? So when you meet a distribution, your first thing is what's your expected value, or what's your mean, and your second question? Yeah, your variance. That's an acceptable question. It's okay to ask, what's your variance? This does not give you the variance. Why are variances so much harder to calculate than means?
Because you need more observations.
Not necessarily more observations. I mean, you do need more. You cannot get a variance from one observation. And this is why a lot of the formulas for sample variance or sample standard deviation divide by n minus 1 and not n, because you should not be predicting a variation when you don't have any variation. Given one observation, I predict this is the mean. Okay, that's fine. And this is the variance. How did you get that?
There's conditional variance?
This conditional, it's the covariance, is that when you're trying to calculate the expected value of a sum, we'll see, is the sum of the expected values. But the variance of a sum is only the sum of the variances if things are independent. And so when you have dependencies, the calculations become a lot harder, and then to get them now is going to be a lot more work. All right, so let me see. I want to try to get straight. So what I want to start off with is the joint PDF. So the PDF is the probability distribution function. The joint probability distribution function means we have more than one variable under consideration. So I want to look at the probability that x equals little x and y equals little y. So I want to know the probability that they both happen at the same time. Now, we will often use, if it's continuous, we might denote it something like f with two subscripts, x and y, to remind us that we have two things under this. And then like that. And then, if it's a continuous random variable, what should the integral of this over all x and y be?
1.
It should be 1. And what should be true about fxy? It should be non-negative, right? If it's discrete, then instead of having integrals, we would have sums. And then we'd have to say the sum over all x and y can only come from a countable infinity. And then we would want all of that. So typically the countable infinities will be the nice ones. 0, 1, 2, 3, 4, something nice like that. That's typically what's going to happen. Now what you could do is you could look at the marginals. How many of you have seen marginals before? Okay. This is, again, one of the challenges when you have a class like this where you have different people coming in from different tracks in terms of what has been said. So I would much rather bore a couple of people a little bit than just ignore something. So the marginals basically just says the following. Screw y, I just care about x. I don't really care about the joint density. So what I would do is I would integrate out y. So y goes from minus infinity to infinity, f, xy, xy, dy. I like to overdo notation. When I have the y down here, it's reminding me that I'm integrating with respect to y. When you have a lot of variables under discussion, anything you can do to help with the processing so you can quickly look down and see what is happening is good. And so this is going to just give us the probability that x takes on the value of little x. So we always use capital letters for the random variables. We use little variables for the values that they take on. Now, in an ideal world, we have the density for x. In a shocking twist, no, there's no shocking twist, right? It's the same calculation if you want to find the marginal for y. You just integrate out now x. In your dream world, we have three densities, right? How would they be related in your dream world? Could it be a sum? Could this be the sum of those two?
Would be multiplication.
It would be multiplication. What would be the danger if it was a sum?
Those would both be ones, then that would be 2.
Yeah, this integrates to 1 with respect to x, this integrates to 1 with respect to y. I'm not even sure what's going to happen now. But if you take a product, so if independent, then the joint density of xy is the product of the marginals. That's a really good notion of independence. Knowledge of y gives you no knowledge of x. And if you want to calculate, well, what's the probability I have the pair x and y? It's just two independent calculations. What's the probability I have x? What's the probability I have y? Most of the time, is this true? No. Right? And that's where things get complicated, is that for a lot of things, the joint density does not factor. How many of you have taken multivariable calculus? Okay, just making sure everybody's hand goes up right now, because this is a prerequisite for the course. Okay? We only can do really two things in multivariable calculus. What are the two techniques we have in multivariable calculus? I think I've said this before. We have two tricks, two techniques.
I think it's like separating it into individual variables. Is that one of the?
It's close to that. I mean, what we would love to do is to have things separated into different variables.
Yeah.
So related to that, it's the changing the order of integration. That's one of the two techniques we have. The other one is changing variables. If you're integrating over a sphere, I would like to suggest you consider spherical coordinates. It may suit your needs very well, especially if your function only depends on the distance from the center. Then it's screaming at you, please integrate over spherical, the angular stuff goes away, and you just have an integration over R. Frequently, and we'll try to see a problem later today, if you switch the orders of integration, it's often easier one way than another. And there's a lot of famous problems they give you in multivariable calculus where you have like e to the x squared y. And if you want to integrate this first with respect to one of the variables, it's bad, but then if you integrate it with respect to the other one, you can make it nice. There's ways to write something down. So here, if things split, then if you want to calculate probabilities, I can do this as two independent integrals, and it's not really a multivariable calculus problem. It's two Calc 1 problems. So as a rule of thumb, as a guiding principle, you would much rather do two easier problems than one harder problem. It's worth doing more simple things than one very hard thing. And this allows us, in many situations, to pass to something easier. All right, so what we want to do is we want to be studying sums. So we will study sums. And maybe we'll let x be x1 plus x2. And we saw examples of what the density was if we rolled two fair die, or if we added two uniform random variables on, say, intervals centered at the origin, and we saw how it converges to the normal as we add more and more things, at least visually. So this is clearly something that is worth studying. You can decide what do you want the variable to be. Maybe instead of x, maybe you call it y2 to denote the fact that it's coming from two things. You have lots of choices. And so one of the questions is going to be, what would be the density for something like this? So what is now, which case do you think is going to be the easiest case? When they're independent or dependent? Independent. So let's do independent. Assume independent. And there's a lot of ways you can do this calculation. I will do the first way by the method of divine inspiration, just write down the answer and try to bully you into believing it's true. And then we'll go through the longer, more casual, more rigorous stroke. So fx of x is the integral from minus infinity to infinity f x1 x1 f x2 x minus x1 dx1. And basically what I'm saying is look at all pairs where x1 is little x1 and x2 is x minus x1, and then their sum, x1 plus x2, is just going to be x. So if I want the sum to equal little x, then the first variable, if the first variable is x1, then the second variable has to be x minus x1. And what's the probability that that happens? It's going to just be this. And I just integrate over all possibilities. If they weren't independent, then what I do is I just have one big function where those are the two arguments. And the hope is that this can be done nicely. And this is such a common occurrence that we will actually say fx is equal to fx1 star fx2. This is the convolution. So I'll write it a little bit more clearer on the next board. So convolution. So f star g of x is the integral from minus infinity to infinity of f of t g of x minus t dt. So whenever you see a definition, you always want to ask a couple of questions. Is this well defined? Now, you can define the convolution in general. You don't have to work with probability distributions. But if they're probability distributions, you have some nice things. And part of the purpose of this class is to give you some insight as to how do you prove things. How many of you have taken real analysis? Okay, how many of you might take real analysis later? Okay, so whichever class you take first, real or abstract is typically the harder of the two because it's your first time really doing a lot of the proofs. And so if I can do anything to try to help those of you who have yet to take those courses, or to help put in perspective those of you who have already taken the course, I think it's time well spent. So if we assume things are probability distributions, what should be true about the convolution? Should it be a density? It should be a density, right? Because if I'm claiming that this is the probability that we get x1 plus x2 equals x, then it has to be a density. So we have to show that it's non-negative, we have to show that it integrates to 1. It's clearly non-negative, because these are non-negative, so clearly non-negative. So if f and g are densities, then 1, it's clearly non-negative, and 2, the integral from minus infinity to infinity of f star g of x dx it equals 1. I'll let you do the calculation, but basically, if I now put in the integral over x, I just switch orders of integration. I integrate over x first, so it's switch orders. And note that the integral x goes from minus infinity to infinity of g of x minus t dx is the same as the integral from minus infinity to infinity of just g of u du, which equals 1. Then I can just translate. And so if I integrate this with respect to x, I switch orders. The integral of g is now 1, and now I integrate f of t dt. That's 1. Okay. Now there's another nice property convolution has. So this is the convolution of f with g. Instead of doing f star g, what could I have done?
G star F.
I could have done g star f. Do you think that this is the same as g star f? What do you think? Yeah. And you can prove it algebraically by doing a change of variables. It's not exciting, right? You're doing algebra. If we can ever avoid algebra and have story time, can you give me a story as to why they're the same? So this is the probability distribution of x1 plus x2. What's the other one?
x2 plus x1.
How is x1 plus x2 related to x2 plus x1? Yeah, can you switch the orders of summing without changing? Yes. Isn't that a much better proof than the algebra? And it gives you an idea of where things come from. Now, if f and g are no longer probability distributions, then the algebra may be the way you have to go. Because we no longer have the interpretation that this is the sum of two independent random variables.
Can we like kind of interpret it as like we're integrating f? So f goes from negative infinity to infinity, and then g goes from infinity to negative infinity. It kind of like goes the other way. So then when we switch the order, it would be the same.
Right, but you're trying to do an algebra proof of that. You're basically doing the change of variable without writing down the change of variable. You're just saying it out loud. But that's essentially the proof. You would then say, replace t with like x minus u. And you have this. So it's the same thing. Yes, yes. So the story, I really like the story approach. So it all comes down to, can we really interpret this as I've claimed? And is it really going to just be the correct way of looking at the probability distribution? So I think you had a CDF problem for your homework assignment. I will admit I occasionally give you just cookbook problems and busy work problems. It's one of the nice perks of being a professor. You can do stuff like this. It's really fun. Every now and then, though, these problems are actually meaningful. And this problem basically allows you to generate any nice random variable if you can generate the uniform random variable, so long as the inverse CDF is nice. So this was actually not a cookbook problem. It's one of the most important ways we have of generating random variables. And so, the CDF method is extremely powerful. If you know the CDF, you know the density. So let's say x is uniform on 0, 1. No, let's do a little bit better. Let's say fx of x is equal to 2x, 0 less than equal to x, less than equal to 1, 0 otherwise. So this should be non-negative, and it integrates to 1. And I could say, let's let y be x squared. And let's calculate what is the density of y. So I think this is in one of the lectures that I just had you watch and do purpose. It's worth seeing again. So let's go very slowly. Let's calculate the probability big Y is less than equal to little y. This is the same as the probability big X squared is less than equal to y. This is the same as the probability negative square root of y less than equal to x less than equal to the square root of y. For our particular problem here, I don't have to worry about negative square root of y because x has 0 probability of being negative. But I just really want to drive through. So this is the probability that x is less equal to the square root of y. This is just going to be the cumulative distribution function of x evaluated at the square root of y. Can you calculate what big F is knowing little f? Yes. Is this a challenge? No. Do you want to calculate it right now? I don't. Do we need to calculate it? No. And this is the power of the method. This is the same as the cumulative distribution function of y. So if we want the density of y, we just take the derivative of both sides. What's the derivative of big F? Little f. So just be little f of x square root of y. But now it's a chain rule time. We have to take the derivative of the square root of y, which is going to be 1/2 of y to the minus a half. And we know that the density is just, input is just twice input. So the 2's cancel. We get, I think, square root of y over y. So I think we actually just get 1. That'd be interesting. get why? So I'm saying
2 times square root of y times 1 over 2 times y to the negative 1/2 in the denominator. So the y to the negative 1/2 goes to the top, and that becomes y to the 1/2.
So the y to the negative 1/2, I don't think is in the.
no, I think it's in the numerator. I think it's in the numerator.
Oh, okay, never mind.
So I think it actually does come out to be 1.
Yeah, you're right.
I mean, at least, it's non-negative, it integrates to 1. So as a nice check, I would actually just go through and see if you simulate this, if it actually does look like the uniform random variable. So the algebra definitely comes out to be 1. So this is the CDF method. If you can calculate the CDF, then it's just a derivative away. Sounds like a vacation, right? Just a derivative away and you get to the density. So now we want to look at what's going on with studying the sums. And I claimed this convolution formula. And so we want to play the same game using the CDF method. So I'll start a little bit further over here. So we'll say x is x1 plus x2. And we want to calculate what is the probability that x is less equal to little x. Right? So how would we do this?
Are we working with the same effect, or?
Well, we'll assume independent. So we have 2 independent random variables. We want to calculate the probability that big X is less equal to little x. So this is going to be the probability x1 equals x1, and maybe x2 is less equal to x minus x1. There's lots of different ways we can write this. And then but x1 has to be free. So should it be like an integral or a sum sign? So let's do it really slowly. We have some space. x1, x2, dx1. Actually, I'll do dx2, dx1. So we do the x1 integral last. This is how we find the probability of an event. Right, I want to go very slowly. This is an event. This is the event that x1 plus x2 is at most little x. So this is the probability that x1 plus x2 is at most x. So we'll forget about whatever that was over here, and we'll write it down more mathematically. So this is my density. I have to integrate over all p as x1 and x2 such that their sum is at most little x. Oh, that's okay. Then that's going to be x1 goes from minus infinity to infinity, and x2 goes from minus infinity to x minus x1. And that will be the same thing here. And that will be the CDF of the sum. Now I want to take the derivative with respect to little x. So then I get the density. And now, this is where it would be wonderful if you had a rigorous multivariable calculus class. I want to take the derivative with respect to little x. I have an integral with respect to x1, and then an integral with respect to x2, with x as one of the bounds of integration, and I want to differentiate this. Let's do it slowly. So I'm going to have d by dx. The integral x1 goes from minus infinity to infinity. Let's assume that it's independent. So it's f of x1, f of x2. Well, I can pull the f of x1 outside the x2 integral. And in the x2 integral, well, the integral of, so this should be, so it'll be x1, x2, this will just be the cumulative distribution function of x2 at x minus x1 minus the cumulative distribution function of x2 at negative infinity dx1. Right? Because I can do the x2 integral. It's the antiderivative. This is why it's so nice that the density splits. Do I really need to keep the cumulative distribution function at negative infinity? What's the cumulative distribution function at negative infinity? 0. So this is just 0. And so now, this does depend on x1, but if I pass the derivative with respect to x through the integral, it just hits this. And so now, I would get, it's the integral x1 goes from minus infinity to infinity, f x1 of x1, and now when I take the derivative here, I will get the little f of x2, evaluated at x minus x1, and I'm taking the derivative with respect to x, so the derivative of the inside piece with respect to x is?
Minus x1.
No.
It's just y.
We're taking the derivative of x minus x1 with respect to x. What's the derivative of x minus x1 with respect to x? It's just 1. And then we still have the integration with respect to x. And that's the convolution formula we had earlier. So this is a more rigorous way to see where that convolution formula comes from by looking at a nice event, the probability that the sum is at most little x. If we had 3 variables, there would probably be some kind of triple convolution going on. We've talked a lot about using parentheses, and if you have more and more things, you can just keep putting parentheses around more and more things, and it's not a big deal. This is one of the key formulas in the class. So either here, or as we wrote it over here, that, that the probability density of a sum is the convolution, if independent, of the 2 probability densities. This is extremely nice. And later when we try to prove the central limit theorem, it turns out that there's something called the Fourier Transform or the moment generating function, and they both are wonderful with respect to convolutions. If you convolve things and apply either one of these processes, it actually splits and it separates, and that's why we're going to be able to make success later on. Right. Any questions about what we've done here? So the most important part is to remember this formula here. Assuming independence, that's going to be our answer. Okay. So the big theorem, and it's always a question of how much do you want to write in your notes. This is all in the book. I did not really plan this part of it because I hate this part of the lecture, but it's got to be done. So theorem. Let me see how general. Yeah, I want to see how. Thank you. I want to see how general I want to make this. I'm going to do. All right. x1 to xn are random variables. g1 to gn are nice functions. Every expected value below is finite, then the expected value of g of x1 plus plus g of xn is the expected value of g of x1 plus the expected value of g of xn. So this is linearity of expectation. What are we not assuming?
Independent.
We're not assuming independence. Not assuming independence. Okay? If we assumed independence, the thing would be far less useful. What's wonderful is this works in great generality. So, do you really want to prove this for n variables? Good answer, right? The answer is no, Professor Miller. We do not want to prove it for n variables. So we will prove it just for 2, and if you can do it for 2, then you can do grouping. Or you can just argue similarly, it's the same idea. So to keep the notation to a reasonable level, we will just do it for 2 things. All right. So proof. So the expected value g x1 plus g x2. And now here's the thing. Do you really want to do g x1, g x2? Do you want to do x1 plus x2, and then you just shove in the g's later? There you go. Right? You're getting all these problems correct. You know. And just for the record, no one is being coerced to saying these things. These are all being done voluntarily. Okay? It's the same argument. All right, so let's look at what this means. It's going to be the integral. And I'll be a little vague right now over x1 and x2. Then we're going to have x1 plus x2. And then the joint density, fx1, x2, x1, x2, dx2, dx1, x2 goes from minus infinity to infinity, x1 goes from minus infinity to infinity. All right, so when you look at this, how many integrals do we have?
2.
2. Right? We have the integral of x1 times this, and we have the integral of x2 times this. I'm only going to do one of the two. The other one is similar, right? Eventually I will prove something, I promise. I'm not going to just keep throwing everything away. So x1 goes from minus infinity to infinity. x2 goes from minus infinity to infinity. x1, and then the density, x1, x2, x1, x2, dx2, dx1, plus a similar piece. Now when we do this integral, we do the x2 integral first. So this is the same as the integral x1 goes from minus infinity to infinity, x1. And now I have the integral x2 goes from minus infinity to infinity of the joint density, x1, x2, dx2. And then after I do that, I then have the x1 integration, plus the other piece. You can see it's just a lot of algebra to write, but the idea is not that bad. What is this integral going to be? I integrate this, x1 is fixed, and x2 ranges from minus infinity to infinity. So what does this integral equal? So we said what this integral was earlier in class today. We fix x1, and we integrate out x2. So what is that called?
Marginal.
It's called the marginal. This is just going to be the marginal of x1. And so just continuing, it's going to equal the integral x1 goes from minus infinity to infinity of x1, and then we'll just have the density of x1 dx1 plus a similar piece. And now what is that integral? That's just the expected value of x1. And so this really is a perfectly acceptable proof. This is not just, I don't know how to do the more general case, I'm trying to bluff my way. There's nothing that changes. All that I would have is I would have g of x1 floating around. Not a big deal. The other integral is handled the same way. Not a big deal. Now, for the other one, you do have to be able to switch the orders of integration. Okay? If you had more terms, not a big deal. So nowhere did we need to use linearity. Could we have used linearity? Not linearity. Nowhere did we need to use independence. Could we have used independence? Sure. We could have written that the joint density split. That would have made the calculation easier. It's still true. But the theorem would not be as useful if it was only applicable when things are independent. And so what I want to do is spend the rest of the time trying to just give you some examples of how you can use linearity of expectation to estimate things. Okay? So any questions on the calculation first before we do linearity of expectation? applications. So who knows why 17 is such a great prime? Goes back to your geometry, yes?
It's a Riemann prime?
Not a Riemann prime, but it is a special type of prime. You are close. It's a Fermat prime. This is, I think, what the tipping factor was that made Gauss become a mathematician. So the nth Fermat number is 2 to the 2 to the n plus 1. So let's make a table. N, Fn. So when n equals 0, 2 to the 0 is 1, so you get 3 is 3 prime, yes. When n is 1, you get 2 to the 2, which is 4 plus 1 is 5, it's prime. Now these numbers grow fast. When you take 2, you get 2 to the 4th plus 1, which is 17, also prime. When you take 3, you get 2 to the 8th, which is 256, plus 1 is 257, which is prime. When you take n equals 4, 65,537, I think? Yes. It's also prime. When you take n equals 5, the answer is no. 6, no. We actually believe that there are no more Fermat primes. That this is it. These are the numbers where if you want to construct a regular n-gon with n sides that are all the same and all the internal angles the same, you can do it only if your n is a product of Fermat primes times 2 to whatever power. So you can't do a regular 9-gon. You can't do a regular 7-gon. You can do the regular 17-gon. And Gauss was the first person to come up with an explicit way to do it. This is a chance to give you a life lesson. Just because you can do something does not mean you should do something. There is a thesis where somebody explicitly constructed the 65,537 con. When I was in grad school, how many of you have heard of Morley's theorem? Wonderful, wonderful theorem. Take any triangle, trisect the angles, and you get 3 points of intersection. And if you look at the 2 lines that are closest to each side, what kind of triangle does it always generate? Equilateral. So I bet one of my friends on this, because I remarked as we were walking to the department, oh yeah, this is trivial to prove. You write down the coordinates of the points, 0, 0, 1, 0, x, y, calculate the squares of the lengths and show that the squares of the lengths are equal. And so he bet me, not that I couldn't, but that I wouldn't have the patience to finish the calculation before graduating. So if I win, he owes me dinner not to exceed $12.50, with grad students, If I lose, I buy him ice cream not to exceed $2.50. And about a year and a quarter, year and a half later, I gave him the proof. It turns out the easiest angles to use is like the tangent of 1/3 of these angles. You get a polynomial degree like 48 to 50 in these. You expand everything out, and then you show that the polynomials have all the same terms, so they must be the same length. And we will not use Mathematica to expand. So I do this as a reminder that just because you can do something does not mean it should be done that way. It's nice to know that there's an answer. It's nice to know here's a proof of Morley's theorem. The great John Conway, who you might know from the Game of Life, he had a beautiful proof. He starts off with an equilateral triangle and reverse engineers to get the triangle you wanted. It's a much, much better proof. It's like half a page to a page of beauty, rather than 50 pages of computer printouts. So these numbers are extremely interesting. We do not know how many there are. We believe there's only 5. I'm going to give you a quick heuristic that there are only 3. Yes, thank you. So you might be a little concerned that my heuristic is that there's 3 when I can actually write down 5 of them. This is the danger of small numbers and small values. So what I want to do is the prime number theorem. And it says here, if pi of x is the number of primes p less than or equal to x, this is approximately x over log x. So in some sense, the probability that a number n is prime is approximately 1 over log n. Now, it's a technical term, this is bullshit. Okay? What is the probability a specific number is prime? Well, it's either prime or not. This is a deterministic system. You know, we're not going to vote on whether or not 5 is prime. Right? I know there's been some pushes to do various things. We're holding the line here in math. 5 will be a prime. It will always be a prime. There was a paper that was just submitted to the Journal of Number Theory that began, perhaps it is time to redefine what it means to be prime. And the editorial board's response was, no, we are quite happy with our definition of prime, and we will keep our definition of prime. But, and this is, yes?
What was he arguing?
I can send you the abstract where he talks about, no, I don't want to say this with this camera. I'll wait till the class is done before I comment about it. I will just say that we've decided that we are quite happy being traditionalists and staying with the notion of prime. What you can do is you can take a deterministic process and you can model it with a random one. And then the hope is that the deterministic system is well modeled by the random one. So let's let xn be 1 with probability 1 over log n and 0 with probability 1 minus 1 over log n. And we can use this to model primes and talk about stuff between primes. Now this is not a great model because if a specific number is prime or composite, it does influence the numbers near it. You know, walk before you can run, baby toy model, see what you can get from it. So let's let the script n be x1 plus x2 plus xn. And we'll just sum these numbers and we'll try to figure out what is the number of Fermat numbers up to n. And now, of course, we might want to go all the way up to infinity. Hopefully the sum converges. And so what would be the expected value of fn? It would be the sum, k goes from 1 to n, of the expected value of xk. And here, what is n going to be? We've got to be a little bit careful as to what I want n to be. I want this to be the nth Fermat number. So really, I should have this as f1, f2, all the way up to fn. And this would be f sub k. Because I want to count how many Fermat numbers do I expect to be prime up to a given point. And if we say being a Fermat number is independent of being prime, if they're just two independent processes, this is not necessarily a terrible model. So this would be a sum, k goes from 1 to n. Now the expected value, well, since it's 1 with probability 1 over log n and 0 with that probability, it's just going to be 1 over the log of the number. So it's 1 over the log of 2 to the 2 to the n plus 1. Or I guess 2 to the 2 to the k plus 1. Alright? And now we start noting, because we've got 5 minutes left in class. If k is large, does the plus 1 really matter?
No.
No. Right? So we're going to start approximating things. And if you do a little bit better job approximating, then maybe you can actually do a little bit better job than the absurdity of that there's only 3 of them. But you get the expected value of fn should be approximately the sum k goes from 1 to n of 1 over the log of 2 to the k. Just drop the plus 1. Well, that's just the sum k goes from 1 to n of we'll have 1 over 2 to the k log 2. And then actually, we should be starting not at 1, we should start at 0. Apologies, switching the place. All 1s become 0s. All roads lead to Rome. So now we have a sum of 1 over 2 to the k. What's the sum of 1 over 2 to the k? It's a geometric series. It's 1 plus a half plus a fourth plus an eighth. What does that sum to? I'm sorry?
It's like 1 minus 1/2 to the n over 1 minus 1/2.
Wait, but just think about it. It's 1 plus a half plus a fourth plus an eighth plus a 16th.
Oh, are we going to infinity?
We're going to, oh, so that's the question now. Are we going to infinity or not? What do you think? Let's go to infinity.
Oh, then it's just 1.
Right? And we'll put the 1 over log 2 outside. Because if n is large, this series is converging so rapidly, just send it to infinity. And then when you do that, you get 2 over log of 2, which is about 2.88. So we predict that this should be on the order of about 2.88 from our numbers. Okay. Given that there are 5 from our numbers, there's a little concern about this model. Now you could ask, well, how bad were the approximations? Maybe for smaller numbers, maybe there's a little bit more likelihood of being prime. Okay. Maybe the model should somehow take into account, oh, I don't know that there are 5 from our numbers in the beginning. And this might be a good idea of modeling the randomness later on. But what you're getting here is that it's an answer that's finite. It's not growing with n. We're not predicting infinitely many from our primes. So it's wonderful to be able to get a prediction like that with this level of work. All right, any questions about this? We have time for one last example. Let's just start it. So this is the Buffon needle problem. How many of you have heard of Buffon's needle? Okay. So there is no need to believe in God to be a mathematician, but the great Paul Erdős said you must believe in the book. So there is a book of ultimate proofs of every theorem in mathematics. And the highest praise you can give somebody is your proof is book-worthy. And some theorems are so important and have so many beautiful proofs, you can have multiple entries. And a few years ago, a couple of mathematicians actually wrote a book titled Proofs from the Book, where they collected what they thought were truly spectacular proofs. How many of you are planning on doing a math colloquium at some point in your life? Okay. If you're, I can't raise my hand for. If you are looking for topics for math colloquium, Proofs from the Book is a wonderful source of place to go to see things. And so there's a lot of proofs. They have 6 proofs of the infinitude of primes, and one of them actually even uses Fermat numbers. Beautiful. One of their proofs is Buffon's needle. So imagine you have a grid of vertical lines that are all d units apart. And it goes off to infinity. And you have rods of length L. And you drop the rod on the grid. And maybe you drop a huge number of rods. Maybe you drop big N rods. And you want to know how often do the rods hit the grid. Yes, it's possible the rod falls perfectly aligned, but that happens with probability 0, so we will ignore it. So most of the time, the rods might, if it's small, it won't hit at all. If this is the size, I can't hit more than one grid. I can't hit more than one grid line. And the question actually involves pi. There's a beautiful geometry to it, so we'll probably do more on this problem later. There is a 2-variable approach to doing this, and then there's a proof from the book where you avoid integrating. It's absolutely spectacular, and we will cover that. One of the things that was nice about this is somebody claimed to have done the experiment and calculated pi to 8 digits. And so they said, that's fascinating. If you tossed one more rod, no matter how it landed, you would have lost 5 digits of accuracy. It's almost as if you do a good rational approximation for pi and chose those numbers for your experiment. Now, I'm not saying you lied. I'm just saying it's amazing how similar that is. So the first thing I want you to note, and that's all we're going to have time to do today, is that the answer is going to be some function of L over D. And the reason is, if I want to count how many intersections there are, if I double D and double L, is it going to change anything? No. So the answer has to depend only on the relative ratio of L and D. If you want, you can make either L or D 1, and it's not going to change anything. And this is the beginning of dimensional analysis. We'll do more on this. Is can you look at a problem and try to capture some of the key features?
So when we're dropping it, after it drops, are you only looking at 2D or 3D?
Only looking at 2D to see where it lands. And so I will end with the following to be immortalized for all posterity. When I was the undergraduate president of one of the undergraduate presidents of the Yale Math Club, my job was to get speakers, and I asked my probability professor, whom I of course held in high esteem as you do every probability professor, would you give a talk? I said, sure. And he gave a talk on Buffon's needle, and he took some spaghetti, from a box, opened the box, threw it up in the air, and saw it land on the floor. Because I had told him, I'll provide the pizza, I'll do all the cleanup. And he said, now, Steve said that he would do all the cleanup. Let's see what happens if you look at wet spaghetti. And he actually got wet spaghetti to stick to the ceiling. I mean, it was well played.